In this lesson, we will begin to study the graphs of our 6 trig functions. We'll begin with the graphs of the sine and cosine functions. Now, we first must understand that our trig functions are periodic functions. Here is the definition for a periodic function. A periodic function, f, is a function such that f of x is equal to f of x plus np for every real number x in the domain of f, every integer n, and some positive real number p. The least possible positive value of p is the period of the function. Now, I want you to understand that when we say it's a periodic function, what we mean by that is these functions, like sine and cosine, start to repeat, their values start to repeat in regular intervals or periods. Phenomena that repeat with a predictable pattern, such as tides, phases of the moon, and hours of daylight, can be modeled by sine and cosine functions. These functions are periodic. Their values are repeating in regular intervals or periods. Another example is maybe like the graph of a normal heartbeat, right? All of these are cycles or functions that have their values repeating in predictable patterns. Now we know the circumference of the unit circle is 2 pi. So the least value of p for which the sine and cosine functions repeat is 2 pi. Therefore, the sine and cosine functions are periodic functions with period 2 pi. That means every 2 pi, the function values for sine and cosine will start to repeat. What I would like to do now is graph the sine function and then jot down some observations, and then we'll move to the cosine function and jot down some observation from its graph. All right, to get us started with the graph for the sine function, I want us to consider particular x values and find the corresponding y value. All right, I filled in my column for my x values that I'll be plugging into the function. These are my input values. I need to consider my corresponding output values. I chose to input angles measured in radians. You could have used degree measure if you'd like. So here we go. We're going to go ahead and plug in values. Now notice that I went from 0 all the way to 2 pi. And also notice I included the special angles in quadrant 1 and all of our quadrantal angles. Okay, so please notice that. All right, here we go. So first, 0. Sine of 0 is 0. And you can confirm all of this by looking at your unit circle. Pi over 6. Sine of pi over 6 is 1/2. Pi over 4. Sine of pi over 4 is root 2 over 2. These are your function values. Sine of pi over 3 is root 3 over 2. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. And sine of 2 pi is 0. Notice that we get these x-intercepts, 0, 0, pi over 2, pi, 0, and 2 pi, 0. These 3 x-intercepts. I know they're x-intercepts because the y values are 0. Also notice that the largest y value, the maximum if you will, is 1. That's the largest y value. Also notice that the minimum, the lowest y value, is -1. We already know that the domain for the sine function is all real numbers, and the range is between -1 and 1. And you can see that being manifested here. The lowest y value is -1. You don't get anything less than -1, and you don't get anything greater than +1 in this entire list. Now, you can keep on plugging in values after 2 pi if you'd like, but because the sine function is a periodic function, you're going to get these same function values to repeat. I'm going to say that again. I only plugged in values between 0 and 2 pi because remember the period is 2 pi. So if you go more than 2 pi, if you plug in 3 pi or, 7 pi over 2 or whatever, all of these function values are just going to repeat themselves. All right, I've created my Cartesian plane as follows. I went from negative 2 pi all the way to positive 2 pi. Now, I know we only plugged in values starting from 0 to positive 2 pi, but I'm going to show you another cycle or another entire period on this side, just to show you that things are repeating. All right, the highest I went on my y-axis is 1. The lowest I went is negative 1 because I know about the range. All right, here we go. I am going to be plugging in these points. 0, 0, which is the origin. The next couple points will be kind of difficult to show. I mean, pi over 6, 1/2. I mean, pi over 6, this is pi here. And so that means this is pi over 2, which is 3 pi over 6. So 1 pi over 6 is right in here, and you're at 1/2. So you're going to be going up, okay? But it's going to get kind of messy, so I'm going to skip that. Pi over 4, root 2 over 2. If this is pi over 2, pi over 4 is right in the middle, and you're at root 2 over 2, a little bit higher, right? Pi over 3, if this is pi over 2, then pi over 3 is right here, a little bit closer to pi over 2. And now you're even higher, you're at root 3 over 2, right? You're getting really close to 1. You finally get 1 as an output when you consider pi over 2. This is pi over 2, and the output is 1. Let me see if I'll show that one for sure. This is pi over 2, and that's the output of 1. All right? Now, pi, you're back on the x-intercept, the x-axis at an x-intercept, pi 0. And then you have 3 pi over 2. That's what this is, 3 pi over 2. You're at negative 1, so now you've dipped below the x-axis here. And then back at the x-axis for 2 pi. So I want you to see that this is the shape of the graph of the sine function. Now, this is only this is one period. This is one period from 0 to 2 pi. You start at an x-intercept, you increase between 0 and pi over 2. Between 0 to pi over 2, you are increasing. And then after pi over 2, you start to decrease, right? You hit another x-intercept, and you decrease all the way until you get to 3 pi over 2, and you start to increase again. So that's the pattern, okay? X-intercept up to a maximum, x-intercept down to a minimum, back to an x-intercept. X-intercept, maximum, x-intercept, minimum, back up at the x-intercept. If you keep on going, this cycle will repeat. This cycle will repeat. So you should be able to continue this way, and that's what I want to show you. So this graph will continue in the same pattern in both directions. This is why it's considered a sine wave, It will continue with the same pattern in both directions. So if we go to the left here, notice the pattern, everybody. Watch this. X-intercept, minimum. Now I'm going right to left, okay? X-intercept, minimum. X-intercept, maximum. X-intercept, what would come next? A minimum. Where? -1. It's a periodic function. After you hit that minimum, you're going to hit the next intercept again. And then after that, a maximum here. And then back to an x-intercept. So I'm going to show you, if you continue, the pattern will be like this. Now I do want to repeat myself that this here is another period. It's another cycle, right? So I've shown you 2 cycles worth or 2 periods worth. Here are a few points that I would like us to consider about the characteristics or features of the graph of the sine function. First of all, it's continuous over its entire domain. What that means for us at this point is we would be able to graph this entire curve without lifting up our pencil at all, right? It's a smooth curve. It's smooth with no holes, no points of discontinuity, no breaks in the graph. That's what it's meant. What's meant by continuous. Okay, it's a smooth curve. There's no holes, no breaks in the graph. Notice that all of your x-intercepts, look at this, -2 pi, -1 pi, 0 pi, 1 pi, 2 pi, and next would be 3 pi, 4 pi, 5 pi. So all of the x-intercepts are of the form n pi, where n is an integer. So basically, all of the multiples of pi are your x-intercepts. The period is 2 pi, so from 0 to 2 pi, you get all the function values, right? You start with x-intercepts, you get your maximum, you get your minimum between 0 and 2 pi. I showed 2 periods here on the graph just to show you what 2 periods would look like, and just to reinforce the idea that this is a periodic function. These function values here are just a repeat of what we've already achieved. This function is symmetric with respect to the origin, right? So there is symmetry here with respect to the origin, okay? And from your algebra studies, you learned that any function whose graph is symmetric with respect to the origin is considered an odd function. So the sine function is an odd function because its graph is symmetric with respect to the origin. What that means is sine of negative x is equal to negative sine of x. Sine of negative x is equal to negative sine of x. What that means, in other words, would be if you consider the opposite of your input, you'll get the opposite of your output, right? Sine of x is your output, x is your input. So if you consider the opposite of your input, you'll get the opposite of your output. Let me see if I can give you an example of what that means. So consider, let's see, sine of, let's do this one. Let's do sine of pi over 2. Sine of pi over 2 is 1. Now, pi over 2 is your input, 1 is your output, right? So the ordered pair here is pi over 2, comma 1. It's on the graph, it's on the curve, it's right here. This is pi over 2, comma 1. I'll label it. All right, that's this point right here. Okay, everybody? Now, because the sine function is an odd function, if I negate, take the opposite of, negate my input, I negate my output. All right, so that means sine of negative pi over 2 should be negative 1, right? The ordered pair negative pi over 2, comma, negative 1 should also be on the graph. And it is. This is negative pi over 2. And look at negative 1 is on the graph. So it is right here. This is negative pi over 2, negative 1. Negative pi over 2, negative 1. So this point is on the graph. That means this point has to be on the graph as well. Okay? These are mirrored images of each other with respect to the origin. These points here are mirrored images of each other with respect to the origin. This point here is positive 3 pi over 2, negative 1. This is negative 3 pi over 2, positive 1. So these are mirrored images of each other. That's what's meant by sine of negative x must be equal to negative sine of x. You see here, this is your input, this is your output. And so this statement here says if you negate your input, which I've negated it now, you will have to negate your output, which I negated my output, right? The opposite of negative 1 is positive 1. And this is all true. These points are on the curve. This one here is 3 pi over 2, negative 1. And this point is negative 3 pi over 2, positive 1. So if you get this point, if you find this point, you get this one for free. If you find this point, you get this one for free, right? That's the meaning of symmetry with respect to the origin. These 2 points here are symmetric with respect to the origin. Pi 0, negative pi 0. They're symmetric with respect to the origin. All right, cool. All right, let's move to the cosine function. We already know that the domain is all real numbers from earlier studies, and we also know that the range is from negative 1 to positive 1. That means it will have the same kind of maximum and the same minimum as a sine function. Here are some input values to consider in radian measure, and so let's go for it. Cosine of 0. Cosine of 0, you can check your unit circle, but you should find that cosine of 0 is 1. Cosine of pi over 6 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 3 is 1/2. And cosine of pi over 2 is 0. Notice that these function values were decreasing in value. You started at 1. This is a little less, even more less, down to 0. So you just decreased in value. From 0 to pi over 2, the cosine function decreases. Let's continue. Cosine of pi is -1. Cosine of 3 pi over 2 is 0 again. And cosine of 2 pi is 1. Notice your x-intercepts. Pi over 2 and 3 pi over 2 are your x-intercepts. Notice your maximum here at 0, 1. You hit a maximum again at 2 pi, 1. And you hit another minimum, at pi. All right? All right, the first point that I will plot will be 0, 1. So that's right on the y-axis. So that's a y-intercept. These points will be kind of hard to show. Just a little bit hard to show. Let me skip down to this one, pi over 2, 0. So pi over 2, 0 is here. That's an x-intercept. So these 3 points that I just skipped here are basically right here, okay, between those two. Pi -1, that's where I'm headed next. All right, I just hit a minimum. 3 pi over 2, I'm back up on the x-axis, and then at 2 pi, I'm back up at a maximum. So then the graph looks something like this. This is the graph of 1 period for cosine. This is the pattern. It started out at a maximum, x-intercept, minimum, x-intercept, maximum. Read from right to left, it is maximum, x-intercept, minimum, x-intercept, maximum. So what comes next? X-intercept, right? It's all about patterns. So an x-intercept should be next if you continue this, and down to a minimum, back up at an x-intercept, back up at a maximum. And it just continues this pattern over and over again. So I've just shown you 2 periods worth of this cycle or of this function. Okay, this is 2 periods worth. All right, here's some observations for the cosine function. First of all, it's continuous over its entire domain, meaning there's no gaps, there's no holes, there's no breaks in the graph at all. You can get the whole graph without lifting up your pencil. The x-intercepts, notice that the x-intercepts are at -3 pi over 2, -1 pi over 2, +1 pi over 2, +3 pi over 2. These are all of the odd multiples of pi over 2, the odd multiples of pi over 2. And so this is how we say that, 2n plus 1 pi over 2, where n is any integer, okay? So here's the first multiple of pi over 2, the third multiple of pi over 2, and another x-intercept would occur at the fifth multiple of pi over 2. This is -1 pi over 2, -3 pi over 2. The next x-intercept would be -5 pi over 2, and so forth. The period of this function is 2 pi, so you get the all of the features of the graph, the important features between 0 and 2 pi. All of those important features are the maximum, the x-intercept, the minimum, right? And you get the entire shape of the graph. If you continue, then you just get that shape again, right? It's just a repetitious kind of cycle, right? Notice that the graph is symmetric with respect to the y-axis. By the way, WRT means with respect to. Notice that the y-axis acts like a mirror. Whatever you see on the right side gets mirrored over on the left side of the y-axis. That means that the cosine function is an even function. Remember, sine was an odd function. Cosine is an even function. I hope you remember from your algebra studies that whenever a function is even, it means that, in this case, cosine of -x is equal to just cosine of x. What this means is if you negate your input, your output remains the same. Even if you consider the opposite of your input, the output remains the same. Let me see if I can highlight this for you. Consider cosine of, let's say cosine of pi. Cosine of pi is -1. Now, if I negate my input, now in this statement, pi is my input. If I negate my input, I should have the same output. Let's see if that's true. So pi, -1, there it is. And negative pi, -1, there it is. It's the same output. It's the same y value. So that's what we mean when we say a function is even. Even when you consider the opposite input, pi and negative pi are opposite inputs on our opposite sides of the y-axis here, then the outputs are the same, okay? Now, there's plenty of points here. I mean, look, this point here is the mirrored image of this point here. So these are mirrored images of each other. So whatever you see on one side of the y-axis, you get on the other. All right, we've reached our first example here. We want to graph y equals 2 times sine of x. Now, I hope to show you by the end of this example that this 2 right here, that is the coefficient of our function, right? It's the coefficient of our function. This 2 will represent, as far as transformations are concerned, a vertical stretch by a factor of 2 units. In other words, our graph will be stretched vertically by a factor of 2 units. So remember that the graph of the sine function has a maximum of 1 and a minimum of -1. The graph goes from -1 to +1. But this 2 here will stretch that out to go from -2 to +2. I'm going to show you that now. All right, I've created a table of values here, and this is a horizontal table as opposed to a vertical one, but notice the first row are some input values I want us to consider. We already know what the sine function looks like, so the reason why I have this middle row right here is I want us to compare our final answer, our final graph of 2 times sine of x, to the parent function, the most basic sine function that we just finished graphing a minute ago. So that's the reason why I have this row here. And I already have it filled out because you and I already did it together. Now, this 2 here basically takes your function values for sine of x, which are listed here, these numbers, and it doubles them and multiplies them by 2. So of course, 2 times 0 would still be 0. 2 times 1 would be 2. 2 times 0 would be 0. 2 times -1 would be -2. And 2 times 0 would be 0. All right, let's graph both of these functions just so that we can compare. Let's graph them both on the same graph, the same plane. All right, this is the graph of our most basic sine function, right? This is what you and I graphed together a little while ago. Now what I'm going to do is graph 2 times sine of x. So it starts at 0, 0. Look at 0, 0. That's what the ordered pair I'm plotting. 0, 0. Pi over 2, 2. This is pi over 2, 2. Okay. Pi, 0. So they do coincide a little bit. 3 pi over 2, -2, and then 2 pi, 0. So notice that the x-intercepts are the same, everybody. Please notice that the x-intercepts are the same, but the height of the graph has changed. The height of the graph has changed. If you continue the pattern, then it would drop down to a minimum over here, another x-intercept, move up to a maximum over here, and then another x-intercept. So what I want you to see is that the graph of 2 times sine of x is just higher and lower, right, than what it would normally be. The x-intercepts are the same. All that changed was the height of the graph. This is known as the amplitude. The amplitude, so here's a definition. The amplitude of a periodic function describes the height of the graph, both above and below a horizontal line passing through the middle of the graph. So here, the line that's going right through the middle of the graph, it happens to be the x-axis. The x-axis is cutting this graph in half, if you will, going right through the middle. The amplitude is the height of the graph above this line, so above the x-axis is 2 units. That's the amplitude of this graph. And it also describes the height below the graph. It's also, the lowest it goes is 2 units below, 2 units below the middle part of the graph, which is the x-axis. So the amplitude is the height. So it can be found by taking the distance from this middle part of the graph, which in this case is the x-axis, and finding the maximum, or from going from the middle line down to the minimum, either way. Now, arithmetically, it can be found by finding half the difference between the maximum and the minimum values. So half the difference between the maximum, and I'm looking at the orange graph here, everybody. So the maximum is 2, and the minimum is -2, right? So then this is basically half of 4, right? Which is 2. So here's the amplitude. I know you could probably just see it as well. Like if you go from the middle line, which happens to be the x-axis, and by the way, the x-axis is not always going to be the line that's going right through the middle of the graph, but in this case it is. So in this case, it's going from your middle line up to the maximum, which is 2 units. It might be clear just to see it, but if you don't just see it, it might be easier in some cases to find half the difference between the maximum and the minimum values, and that will give you your amplitude. So in conclusion, we can think of the graph of y equals a times sine of x as a vertical stretching of the most basic, or sometimes I call it parent function, y equals sine of x, whenever a is greater than 1. Like in this case that we just came from, this a value was 2. And so the graph of sine of x got stretched by a factor of 2. If that value a here in the front is between 0 and 1, so a fraction between 0 and 1, then it's not going to be a vertical stretching, it'll be a vertical shrinking. So before we move forward, I just want to make sure that we're clear that the graph of y equals a times sine of x, or even y equals a times cosine of x, it will have the same shape as the graph of y equals sine of x or cosine of x, respectively. These are the most basic graphs, right? So the shape is not changing, except with the fact that the range is now no longer -1 to 1. The range is now negative absolute value of a, comma, absolute value of a. That is to say, the amplitude is the absolute value of a, the absolute value of that number out front. Look at this next example. Graph y equals sine of 2x. Now notice the 2 is actually part of the argument. 2 is part of the argument of the function. The 2 is not out front as a coefficient of the function as before. The 2 is inside the argument, part of the argument. So I want you to write down this note. The coefficient a in this equation, y equals a times sine of x, or in this equation, y is equal to a times cosine of x, affects the amplitude. We just said that, right? A here represents the amplitude, but the coefficient of the variable x in the argument affects the period. It affects the period. Please note that in your notes, that the coefficient of 2 here, the coefficient 2 of x, represents a change to the period. Let me see if I can prove that for you. So what I'm claiming is that the graph of a function of the form y equals sine of bx, or y equals cosine of bx, will have a period different from 2 pi. The period's going to change. So this is true whenever b, the coefficient of x, is not 1. So let me see if I can prove that for you. Remember the values of sine of bx or cosine of bx will take on all possible values, remember, as bx ranges from 0 to 2 pi. We saw that in the most basic sine and cosine graphs, right? So you get all of your possible values as you let your argument run from 0 to 2 pi. Therefore, to find the period of either of these functions, sine or cosine, we must solve this 3-part inequality here. We must allow the argument to run from 0 to 2 pi in order to take on all the possible values for these functions. So if we solve here for x by dividing both sides by b, 0 divided by b is 0 divided by b is just 0, and bx divided by b is just x, and 2 pi divided by b is 2 pi over b. Therefore, the period here, right, will be 2 pi b, right, 2 pi b. This will be the period whenever the argument has a coefficient other than 1. Your function will take on all possible values as you allow your argument to run from 0 to 2 pi over b. So let's use this information to graph the function that's been given to us, y is equal to sine of 2x. Now, the first thing I like to do many times is to determine what is the period. What's the period? So we just discovered that for sine and cosine, the period will always be 2 pi divided by b. Now, in this particular example, your b value is 2, right? It's right here. That's your b value. So you can see that the period, therefore, is pi. The period is pi. What this means is that the graph will complete one period over the interval between 0 to pi. So remember that for the most basic sine function, the period was 2 pi. So it completed one period from 0 to 2 pi. But now it's from 0 to pi. All right, now that we've figured out the period, what we're going to do next is find the midpoint of this interval, what's right in the middle, and also the quarter points, what's called the quarter points. So follow me here. Let's find the midpoint first. Now, in order to find the midpoint, what you can do is just take half of the sum of the endpoints, right? So what I can do is find half of 0 plus pi, right? This is how I'm going to find the midpoint. Notice that this is the midpoint formula from maybe your algebra studies. So then it's half of pi, which is pi over 2. So the midpoint is pi over 2. Please remember that. The midpoint is pi over 2. What I'm going to do next is find my quarter points. Now, in order to find the first quarter point, what we're going to do is find the midpoint between the left endpoint and the midpoint, okay? We're going to find halfway, the distance halfway between the left endpoint and the midpoint. In other words, in order to find that, what we're going to do is take half of 0 plus pi over 2. This is your left endpoint. This is your midpoint. So then it's half of pi over 2, which is pi over 4. Pi over 4 is your first quarter point, Technically, your second quarter point is already found. It's your midpoint. This is called your midpoint or your second quarter point. Now, what we need last is your third quarter point. Now, the third quarter point would be the distance from, pay close attention, from the midpoint to the right endpoint. Okay, as a reminder, the first quarter point was the distance between, the halfway between your left endpoint and the midpoint, right? Halfway between 0 and pi over 2 is pi over 4. The third quarter point will be half the distance between pi over 2 and pi. So I'm going to go half of pi over 2, that's your midpoint, all the way to your right endpoint, which is pi. So it'll be half of 3 pi over 2, right? Pi over 2 plus pi. Remember, pi is really 2 pi over 2. So this is the sum of these two with a little bit of fraction work is 3 pi over 2. So half of 3 pi over 2 is 3 pi over 4. This is called your third quarter point. Okay? So what we have is our left endpoint, our right endpoint, our midpoint, and our quarter points. Let me put this in order for you. So from left to right, you have your left endpoint, All the way over here on the right, you have your right endpoint, right? We found this interval, again, by finding the period first. So it gave us the interval, so there's our left endpoint, our right endpoint. The first, once we had this interval, then the first thing we found was the midpoint, and then the midpoint between the left endpoint and the midpoint is the first quarter point, and the midpoint between the midpoint and the right endpoint is the third quarter point, right? So this is the idea, you guys. The idea is these are going to be the 5 input values. These are going to be the 5 values that we're plugging into our function, and the outputs will be the maximum, the minimum, and the x-intercepts. Those are the most important features or most important points on our curves. Will be the maximum, the minimum, and the x-intercepts. That's what you'll end up getting by plugging in these particular input values. So we want to be smart as far as what we're plugging into our function. We don't want to just plug in whatever we want, although we could because the domain is all real numbers. We want to plug in the values for x that will give us in return the maximum, the minimum, and the x-intercepts, so then we can just draw the curve through those important points. So here we go. We have our table. We're going to start plugging these values in. Left endpoint, first quarter point, midpoint, third quarter point, right endpoint. Okay? And just in case it helps someone out there, notice that your interval goes from 0 to pi. From 0 to pi. From 0 to pi. Your left endpoint is 0. Your right endpoint is pi. What's right in the middle, of course, is your midpoint, which is pi over 2. So this is just a picture that corresponds with with the work you've done so far with your quarter points and so forth. Your first quarter point is right in the middle of 0 and pi over 2, which is pi over 4, right? Your third quarter point is right in the middle of pi over 2 and pi, which is 3 pi over 4. So this is what you've determined so far. Left endpoint is 0, first quarter point is pi over 4, midpoint is pi over 2, third quarter point is 3 pi over 4, your right endpoint is pi. So here's a picture that corresponds with what we've done so far. All right, let's plug in these values in for x. Don't forget you have to multiply by 2 and then take the sine value. All right, let's do it. When I let x be 0, 2 times 0 is 0, and sine of 0 is 0. When I let x be pi over 4, 2 times pi over 4, let me show you this, 2 times pi over 4, right, would end up being pi over 2, and sine of pi over 2 is 1. So I'm going to let that be 1, okay? Now next we're plugging in pi over 2. But never forget that you have to, multiply your input by 2. So it'll be 2 times pi over 2. So I'll show that. 2 times pi over 2. Oh, that's just pi. And sine of pi is 0. 3 pi over 4 is next. And I have to multiply that by 2, right? Of course, every input multiplied by 2. You would get 3 pi over 2. And sine of 3 pi over 2 is negative 1. This one we could probably do in our head. When we plug in pi, we have to multiply by 2, right? So 2 times pi is 2 pi. And sine of 2 pi is just 0. Notice that you have your x-intercepts here, 1, 2, and 3. You have your maximum and you have your minimum. And that's what I mean. We wanted these input values, these quarter points and left endpoint and right endpoint and so forth. We wanted these 5 input values that were going to give us these important points, these important values. All right, here's our graph, and it's the normal shape, everybody. It's the same shape as the most basic sine function. The big difference is the most basic sine function usually completes this shape between 0 and 2 pi. But now we completed the shape, the entire curve, in a shorter amount of time, right? Between 0 and pi, instead of 0 to 2 pi. So the graph got shrunk horizontally. It got shrunk horizontally. This curve used to finish out way out here at 2 pi, and it finished at pi. So it got shrunk horizontally. So we can think of the graph of y equals sine of bx as either a horizontal stretching or a horizontal shrinking. It'll be a horizontal stretching when b is a fraction between 0 and 1. It'll be a horizontal shrinking when your b value is greater than 1. Like in our case, our b value was 2 and our graph shrunk horizontally, okay? I'm talking about in relation to the most basic sine function. This is the graph that got horizontally shrunk. All right. All right, so in conclusion, whenever b is positive, the graph of y equals sine of bx will resemble that of the most basic sine function, but with period 2 pi over b. Same thing is true for cosine. The period will be 2 pi over b. Okay, everybody? Okay, we're going to look at some examples now back to back, but I wanted to give you some steps or some guidelines to consider. The first thing we're going to do for each of these is we're going to find the period. Once we find the period, we'll have an interval that we're going to split into 4 equal parts. We're going to take that interval and cut it into 4 equal parts. And we do that in order to find the midpoint and quarter points. Once we have our midpoint and quarter points and our left and right endpoints, those are 5 points, by the way. Left endpoint, right endpoint, 2 quarter points, and a midpoint. That's 5 points. We're going to evaluate the function at these 5 x values. And the points will be the maximum, the minimum, and the x-intercepts of the graph. We'll then draw a smooth curve through these points with amplitude, absolute value of a. I'm going to walk you through these steps or guidelines for every single example that we do from this point forward. All right, here we go. Graph y equals cosine of 2/3 x. The first thing I'm going to do is find the period. Now remember the period will be equal to, now I'll just use p for period, okay everybody? 2 pi over b. Your b value in this case is 2/3. That's the coefficient of x. So it's 2 pi divided by 2 pi divided by 2/3, right? Which is 2 pi over 1, really, times 3/2, right? That's how we multiply by a fraction. That's how we divide by a fraction. We multiply by its reciprocal, right? These 2's here divide out, and you can see that your period is 3 pi. Very good. So we can see, you know, the normal period is 2 pi, but now this period is 3 pi. The period has been extended. So that should tell you that this 2/3 represents a horizontal stretching. That's what this is, a horizontal stretch. Okay, now that I know my period is 3 pi, I know the interval over which the function completes one period is now 0 to 3 pi. No longer 0 to 2 pi, 0 to 3 pi. Okay, so what we're going to do is we're going to divide this interval into 4 equal parts. That is to say, we're going to find the midpoint and the quarter points. We already know what the left endpoint is, 0. We know the right endpoint, 3 pi. We want to know what's right in the middle, and then we also want to know the quarter points. I'm going to use MP for midpoint. And the way I find my midpoint is by just taking half of the sum of the left endpoint and the right endpoint. This is the midpoint formula. So this is half of 3 pi. That is to say 3 pi over 2 is your midpoint. I'm going to use QP1 for my first quarter point. I find my first quarter point by taking half of, now watch this, my left endpoint and now my midpoint. Okay, I'm basically finding half the distance between my left endpoint and the midpoint, or the midpoint between the left endpoint and the midpoint. All right, so then this is half of 3 pi over 2, or that is to say 3 pi over 4. Make that a little neater for you, 3 pi over 4. Finally, find the second quarter, or excuse me, I should say the third quarter point, because the midpoint is technically the second quarter point. I should say QP3. All right, in order to find the third quarter point, I take half of the sum of my midpoint, which is 3 pi over 2, and my right endpoint, like this. So then this is half of, now just for fraction work here, remember that 3 pi is really 6 pi over 2. And 6 pi over 2 plus 3 pi over 2 is 9 pi over 2. And so your third quarter point is just 9 pi over 4. 9 pi over 4. And again, I'm trying to make this neater for you. 9 pi over 4. All right, we have our left endpoint. I'll try to go in order here. Left endpoint, our first quarter point, our midpoint, our third quarter point, and our right endpoint. These are the 5 points that you're going to plug into your function in step 3. All right, here we go. Step 3, let's evaluate our function, cosine of 2/3 x, at each one of these values. It's kind of easy to plug in 0 here. When you plug in 0, you let any x be 0, and 2/3 times 0 is just 0. And cosine of 0 is 1. I'm going to show my work for the next ones, though, just to make sure that we're all on the same page. I'm going to let x be 3/4 now. Let me see if I can show this here. 3 pi over 4. I think I said 3/4. 3 pi over 4. There. So notice that some fraction work here, 3's cancel, and then this ends up being cosine of pi over 2. And cosine of pi over 2 is just 0. So then y is equal to 0. Y is 0 when your x value is 3 pi over 4. See, that's an x-intercept right there. It started out with, you started with a maximum, now you're down to an x-intercept. I wonder if you can guess what this would be. If you start at a maximum, you went down to an x-intercept, you should go down further to a minimum, right? That's the pattern. So let's see if we can get the minimum. All right, we are plugging in 3 pi over 2 now. All right, 3 pi over 2. You can see the fraction work here. The 3's cancel and the 2's cancel. You're just left with cosine of pi, which we know to be -1. So there it is. There's the pattern, right? Maximum, x-intercept, minimum. At this point, it should go back up to an x-intercept, so we should get 0 here. All right, I'm plugging in 9 pi over 4. And let's see, this simplifies to 3 pi over 2. And cosine of 3 pi over 2 is 0 for sure. So the pattern holds true. One more to go. Y is equal to, and you should expect, right, a 1 here, shouldn't you? Because maximum, intercept, minimum, intercept, maximum, right, everybody? So we expect to get a 1. All right, cosine of 2/3, and this time times 3 pi. This simplifies to cosine of 2 pi, which is just 1. So the pattern holds true. All right, let's go ahead and graph this. All right, to get us started, I have labeled my axis here, my axes. I start at 0, 1, that's a maximum. I drop down to an x-intercept here, down to a minimum here, back up to an x-intercept, and all the way back up to a maximum. So, oops, let's make that a little nicer. I have something like this, okay? Here is the graph of this function, and it's showing just 1 period, all right? A little sloppy, but I think you get the idea. Notice the amplitude is 1. The amplitude is the height of the graph above your middle line, sometimes called the middle C. I'll explain later why it's called the middle C. For now, I'll call it the middle line, the line that's going right through the middle of your graph, and it's still the x-axis. It'll still be the x-axis for a few more examples. So the height above the x-axis is 1 unit, or the height below the x-axis is 1 unit. The amplitude is 1, okay? This was step 4, by the way. I was labeling my steps, and I guess I failed. Step number 4 is plotting the points and drawing a smooth curve with amplitude 1. All right, here's our next one. Y equals -2 times sine of 3x. As far as transformations are concerned, notice that this 3 right here is going to be a horizontal shrink. That's a horizontal shrink, right? This 2, let's ignore the negative just for a second. The 2 will be a vertical stretch by a factor of 2, a vertical stretch. This 3 will change your period. This 2 will change your amplitude. That's a lot in and of itself, right? So this 3 will change your period, which is the reason why it's a horizontal shrink. And this 2 will change your amplitude, okay? The negative here, it represents a reflection across the x-axis, all right? So that's how this goes as far as transformations are concerned. Let's find the period in step number 1. Let's find the period. So P is equal to 2 pi over B, which in this case is 2 pi over 3. Very good. So this tells me that my interval, I'm just going to go ahead and write it, my interval over which it completes one period is 0 to 2 pi over 3. Now that agrees with what we said a second ago with a horizontal shrink, because usually the interval is 0 all the way to 2 pi, but now it's only 0 to 2 pi over 3. It's a shorter interval. All right, step 2. In this step, I take this interval and I cut it into 4 equal parts in order to find the midpoint and quarter points. The midpoint is half the distance between your left endpoint and your right endpoint. So it's basically half of 2 pi over 3, which is pi over 3. So pi over 3 is your midpoint. Your quarter point should be next. Well, your first quarter point. So I'm just going to say QP1, okay, everybody? Your first quarter point. And this is half of the distance between your left endpoint and your midpoint. You know what I just noticed? This should be a plus sign and that should be a plus sign. Let me fix that. All right, better. So then this is half of pi over 3, which is pi over 6. One more to find, which is your third quarter point. Remember that your midpoint is really your second quarter point. So you already have your second quarter point. So the third quarter point is half the distance between your midpoint and your right endpoint. All right. So then this is half of pi, because 1 pi over 3 plus 2 pi over 3 is 3 pi over 3, which is just pi. So pi over 2 is your third quarter point. In step 3, we're going to evaluate our function at these 5 important points, these 5 input values. All right, I have set this up. I'm going to go ahead and start plugging in here. When you let x be 0, 3 times 0 is 0. Actually, I feel kind of led to show you this. There. So then you get y is equal to -2 times sine of 0. And sine of 0 is 0. So it's -2 times 0, which is just 0. So then this function here starts out here. The graph starts at an x-intercept, the origin. All right, I'm plugging in now pi over 6. So y is equal to -2 times sine of 3 times pi over 6. So this turns out to be y equal to -2 times sine of pi over 2. And sine of pi over 2 is 1. So then your y value is -2. That's definitely a minimum. Usually the sine function from your x-intercept, it increases to a maximum. But in this case, it's decreasing to a minimum. The reason is because of the reflection. It's no longer increasing, now it's decreasing on this part. All right, next let's plug in pi over 3. All right, I went ahead and plugged in pi over 3 and pi over 2. For pi over 3, I got the x-intercept of 0 and then a maximum. So notice the pattern. X-intercept down to a minimum, x-intercept up to a maximum. I should expect an x-intercept again. 2 pi over 3, when you plug it in, this 3 right here that's on the argument will cancel with this 3, leaving you with just 2 pi. And sine of 2 pi is 0, so negative 2 times 0 is just 0. All right, very good. Let's draw the curve. All right, the first point is 0, 0, and I move down to a minimum at pi over 6. And at pi over 3, I'm back up at an x-intercept. At pi over 2, I'm up at a maximum of 2. And 2 pi over 3, I'm back where I started at an x-intercept. And so this is my wave. It's pretty cool. Again, notice that the sine function, usually from the origin, it goes up this way, right? But it's now going downward, and that's all because of the reflection. Notice that the amplitude is 2 units. 2 units above the x-axis or 2 units below the x-axis. And that's because the x-axis, that's because of this 2 here. And also the x-axis is the line that happens to be going through the middle of your graph. Which one will not always be the case, but again, it is the case for these few examples. I'll let you know when the x-axis is no longer the line that's going right through the middle of the graph, okay? It'll be when we look at examples that have vertical translations. All right, our last example like this one, y equal to negative 3 times cosine of pi x. All right, let's find the period. It's 2 pi over b. In this case, it's 2 pi over pi, which is just 2. So the period is 2 units, so that means the interval used to be 0 to 2 pi, now it's just 0 to 2. Okay? Your left endpoint is 0, your right endpoint is 2. All right, let's cut that interval into 4 equal parts. That is to say, find the midpoint. I feel like we don't really need to do the arithmetic. If you need to find the midpoint between 0 and 2, what's right in the middle? It's 1. So I'm just going to go ahead and write it down, 1. Okay. The first quarter point will be the distance, half the distance between your left endpoint and your midpoint. So it'll be half of 1, which is just 1/2. And then your third quarter point will be half the distance, or the sum, of your midpoint and your right endpoint. So it'll be half of 3. So it'll be 1.5. Okay, 1.5. All right, cool. Let's do it. All right, let's do it. When you plug in 0, you end up getting pi times 0, which is 0. Cosine of 0 is 1. And negative 3 times 1 is negative 3. When you plug in 1/2, you get half of pi, which is pi over 2. Cosine of pi over 2 is 0. Negative 3 times 0 is just 0. When you plug in 1, you get 1 times pi, which is just pi, and cosine of pi is negative 1. Negative 3 times negative 1 is positive 3. Notice the pattern. Minimum, x-intercept, maximum. I expect to get an x-intercept again. 3/2. 3/2 times pi is just 3 pi over 2, and cosine of 3 pi over 2 is 0. Negative 3 times 0 is 0. And I expect to end this thing at a minimum. You know, notice that the cosine function usually starts at a maximum, and then it goes down to a minimum. It's starting now at a minimum and going up to a maximum, right? And that's because of this reflection there. Okay, 2 is next. 2 times pi is 2 pi, and cosine of 2 pi is 1. Negative 3 times 1 is negative 3. All right, we're starting this wave at 0, negative 3, and then we have an x-intercept here. We have a maximum here at 1, 3. We have an x-intercept here, and then a minimum again here. So then it's something like this. Remember, these are smooth curves like that, okay? So try to make it a smooth curve. Cool deal. Let's look at another example, and this one will be a little different, and this will wrap it up for us. Okay, this time around, they give you the graph. You have to come up with an equation that matches the graph, as opposed to, you know, all the other examples. They give you the equation. You come up with the picture. You come up with the graph. They've turned the tables on us. Now, they want the equation of the following form: y equal to a times sine of bx, or y equals a times cosine of bx, and b is positive. The reason why they give you some type of guideline as far as what the equation should look like is because there's infinitely many, or there's a lot. Let's just say there's a lot of different ways you can write the equation. Now, there's a few things that come to my mind when I see this graph, okay? One thing that comes to my mind is the period. The period goes from, on the x-axis, goes from 0, right, x equal to 0, all the way to x equal to 4 pi, from 0 to 4 pi. That's longer than normal, right? The normal is 0 to 2 pi, and now this is 0 to 4 pi, so it's been extended, it's been horizontally stretched. So the first thing I want to do is find the period. All right, so this is what I'm going to do. I know that the period is 2 pi over b, right, everybody? And so that tells me, that implies that 4 pi, which is the period, is 2 pi over b, right, everybody? We know what the period is by just looking at the picture. It completes one period from 0 to 4 pi. So I can solve for b here. I can solve for b by multiplying both sides by b, and I'll get b times 4 pi is equal to 2 pi. So what I can do is divide both sides by 4 pi to isolate b and get that b must be equal to 1/2. That's what's going to get my period to extend, all right, to horizontally stretch. Now, okay, I know my b value, that's good, but what else is very interesting to me is, let's see, the amplitude. Usually the amplitude for sine and cosine, for both of them, is just 1, but the amplitude here is 2 units. So I know that, let me, if I can just write that right here, everybody. I know that the amplitude, the absolute value of A, is just 2. That's my amplitude, okay? So that's good. I know A. Now, notice that for cosine, usually cosine starts at a y-intercept, right? Like 0, 1. And usually it comes down, right? It decreases. But here, this is increasing. And so my thought is there has to be a reflection in here somehow, because usually the cosine function is, and the reason why I'm thinking of cosine is because sine usually begins at the origin, and this is not beginning at the origin. So that's why I'm thinking cosine as opposed to sine, everybody. But cosine, again, I'll say it again, cosine usually starts here at 0, 1 and then decreases, it goes down. But here it's starting at 0, -2, and it's going up. And I think the reason why is because of a reflection. So there must be a reflection. So let me take what I know, and let me take this A value, and let me take my B value and see if I can write this out for us. So how about y is equal to, there's my reflection, here's my amplitude, I'm thinking of the cosine function, and my b value must be 1/2 and then x. How's that for you? Cool deal. So this is the reflection, which is the reason why it starts to increase right away. This is my amplitude, the absolute value of -2, which is 2. 2 units is your amplitude. And this b value of 1/2 is going to cause you to horizontally stretch your graph, changing your period. These are fun because you kind of have to do some detective work, so it's a lot of fun. This completes this lesson. It's sort of a long lesson, lengthy lesson, but I hope it was very, very interesting for you. I hope you took really good notes, and I'll see you soon.